Okay guys, we continue from where we stopped last time. We were looking at the concept of equal vectors. So if we have the same direction and the same magnitude, same length, we can say they're equal. So here we've got three vectors A, B, C, D, and E, F in the two-dimensional plane. And as you can see here, they're pointing in the same direction, they're parallel and same magnitude. Therefore, we can say that for the vectors A, B, C, D, and E, F are equal. So we can either use the arrow or the underlining notation to show that what we're talking about. We're talking about vectors. Okay, so that's what we have. We can continue now. Let's look at 5.3.1. So we now look at 5.3. We look at the concept of a position vector. Okay, so a position vector. I won't give a descriptive definition. I'm just gonna give you a pictorial representation of the concept of a position vector. So let's say we have some two-dimensional plane xy, and then we have some particle, maybe let's say some physics, some particle that's moving in some curve. It could be a vehicle, it could be anything, but for now let's just say we have some particle that's moving in some curve. So we have an observer who is observing this particle seated at the origin. So now we'll take the origin to be the initial point, and wherever the particle is, that's where we are going to have our terminal point. So we can have the particle at Q1, we can have the particle at Q2. So as it keeps on moving, this vector keeps on changing. That is what we call a position vector. It actually is giving position to the giving position of the particle as it's moving along the curve. So that is what we call a position vector. So the only concept we need to know is that the initial point of a position vector is usually at the initial point, which is the initial point usually at the origin. So we have the initial point at the origin, so we can denote our vector PQ, or denoted by V. Okay, so that is what we have as our position vector. Okay, so that is the concept of a position vector. Key concept: the terminal point P is at the origin, but we can have a vector anywhere. That will just be a vector, but a position vector, the key thing we need to know is at the origin. So we continue 5.3.1. We'll take some definition, maybe of some representations of some sort. So let's say we have a two-dimensional vector, so a 2D vector in the x or y plane. So we have some x or y plane, two-dimensional vector in the x or y plane with initial point. So the initial point, remember here is how we define it to be at the origin. So with the initial point at the origin and terminal point at some point. So this terminal point can be anywhere. Remember, some point. So we're going to call that point. Give it coordinates v1, comma v2, with v1 being the x coordinate and v2 being the y coordinate. So such a vector is a position vector, and in its component form. So now we introduce the concept of components. So it has a component form. So now we introduce some form. So V, underline it, that's the vector. Q, underline. So this vector is given by this v1, comma v2. But this time around, we're not using circular brackets. We're using angular brackets to represent that we are actually now writing a vector, not a point. So we're not just writing some coordinates, but now we are writing a vector. So remember, don't forget the notation. These are angular brackets, so angle brackets. So that's what we use for representing vectors. Okay. So what if we extend this concept to 3 dimensions? So what happens? So in 3 dimensions, let's say we have a vector with initial point. Of course, the original will be 0, 0, 0, and the terminal point, let's say, let's have v1, v2, and then an extra v3, because now we are in a 3-dimensional space. We have an extra z. So let's say we have that, and let's say we also which means then if we extend the same concept, the component form will now be v1, v2, v3 in angular brackets to represent that we're talking about a vector. And never forget, whenever you're writing, to either use an arrow or to use to underline, just to show that it's a vector and it's not a scalar. So the components, remember, the components are scalars. That's why the v1, v2 are not underlined, because they are scalars. Okay, just some general remarks on what we have learned so far. So let's say we have some general vector with the initial point P at some arbitrary point in the 3-dimensional xy plane, xy space, xyz space. So we have x1, y1, z1, and q, x2, y2, z2. Then the vector, some general vector pq, not really a position vector, but some vector, general vector. We can just, by subtracting the final coordinates, the terminal coordinates minus the initial coordinates. So x2 minus x1, y2 minus y1, z2 minus z1. Then we put them in angular brackets to represent that we are talking about a vector. Okay, so that is how we are going to get your vector. So if you are given that vector, so how do we get the magnitude? So the magnitude of vector pq, we extend the concept of Pythagoras theorem from 2 dimensions, which we can extend it to 3 dimensions. So we have pq, or the magnitude of v, underlined there, okay, is equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, and everything we get a square root. Okay, so that's how we get the magnitude of that. So generally that's what we have. Then the other thing we need to note is that the only vector with a magnitude of 0 is the 0 vector. So if we have a vector of pq with magnitude which is equal to 0, that will be 0 vectors. So that's how we represent the 0 vector. It is 0 with an arrow, or 0 with underline under, or using angular brackets if you have a 2-dimensional 0 vector, or if you have a 3-dimensional 0 vector. So you have 3 zeros, 0, 0, 0, and in terms of direction, the 0 vector is the only vector without a specific direction. So there's no specified direction for a 0 vector. Okay, so that's what we get. Okay, since we are progressing well enough, sorry for that recording. Okay, we continue just to give extra meat to what we're just from learning. Maybe we can consider looking at an example. Okay, so let's see, guys. Let's see how everything is moving. So let's look at an example. Okay, let's look at an example. So we have so that this should be 5.4. So 5.4. We look at example. Okay. So find find component form. So find component form. B, find the length, or other terms, the magnitude of a vector of a vector with initial point, p at -3, 4, 1, and terminal point. And we can also create the final point, and the final point at his q at -5. That's -5, comma 2, comma 2. Okay. So that's the question. A vector. So from given initial point and final point. So let's find the component form. Let's also find the magnitude. So A. So we can call this vector. So remember V1, we subtract the x coordinates. So we subtract this. So the final minus the initial. So it's -5 minus 3. So that gives us -2. Then the y coordinates, y2 minus y1. That should give us 2 minus 4 rather. Gives us -2. The z component, V3, should be z2 minus z1, which should be 2 minus 1, which gives us what? 1. So therefore in component form, with the new notation for angular, so our vector PQ, or a vector V, we can call it, so vector PQ, so, we're finding the component form at the magnitude yet. So underline it, PQ is equal to, you can also name it as V, so it will just be -2, -2, 1 with the angular brackets notation. Okay, so B, we're asked to find the length of the vector. So how do we get the length of the vector? We have got the components, so we can have the components, so we can just apply Pythagoras theorem, the one we just looked at, and then finally we have that -2, everything is squared there, plus 1 squared to get a square root. That should give us square root over 9, which is equal to 3. So thank you very much, guys, for being with us. See you in the next class. Okay, bye-bye.